Hello, everyone, and welcome to another online learning day. If you are doing this video on the day it is assigned, it is January 29th. So, welcome to near the end of January. Let's get into it. Our focus for today, our essential question that will guide our learning is: how do I use dimensional analysis, DA, to solve problems with chemistry conversions? So, we already learned a little bit about DA last time, where you set up a given, you cancel units to get to whatever unit it's asking for. And that problem solving process is really best used with complicated problems with lots of conversions. And so, what we need to start doing is putting it into chemistry context. So, now we kind of know how to do DA, but that seemed random. So, now let's learn how to put chemistry things in it so that we eventually can start preparing for complicated conversions that involve chemistry things. So, that's where we're going with this. Before we do that, though, why don't we do a quick bell ringer warm up that reviews dimensional analysis in general. So let's pretend it is someone's birthday today. Maybe it is someone's birthday today. Happy birthday to you. How many grams is a 3.4-pound birthday cake? So I just happen to want to know how many grams it is. So I start with my given and I write that down. So start with your given. Go ahead and do this with me instead of just watching. That doing together will help you learn this a little bit or review it. 3.4 pounds is my given. I want to know how many grams it is. So I need to find a conversion that will get rid of pounds and get me closer to grams. So I set up my brackets. I want pounds to cancel. So it has to be in the opposite spot of where it is now. Top here, bottom here. If you look at a list of conversions, it turns out that there's 2.2 pounds for every 1 kilogram. All right, well, that must be related to grams. So pounds will cancel. I'll be left with kilograms, but I don't stop there because I want to get to grams. So we look at our metric conversions, and I know that kilo is 1,000 times bigger than the base unit. So that means I'm putting kilogram on the bottom so it cancels. 1 kilogram equals 1,000 grams because kilograms are bigger than grams, so grams fit into kilograms. Kilograms cancel. Yay, I'm at grams. Equal sign, because that's what the problem is asking for. Multiply numbers on the top, divide numbers on the bottom, you get a calculator answer. Oh, but that calculator does math, not science, right? So we got to think sig figs. This has 2 sig figs. This has 2 sig figs. This is a definition, so there's no error in this measurement. So there's no sig figs needed there. So I can keep 1, 2 sig figs. I look at this number for rounding, which it does not. So then these turn into placeholders. 1,500 grams of cake. Yummy. That's a lot of cake. All right. So that reviews dimensional analysis in general. But what we're going to add in today is, well, what if we have chemistry conversions instead of just random things like grams and kilograms and cake and stuff like that? All right. So go ahead and set up your focus notes for today. So our topic is DA and the chemistry mole. And our official essential question for our notes is, what is the chemistry mole and how do I use DA with mole conversions? Now, mole might be one of those things that when you talk to people who have had chemistry, like maybe other family members or friends, mole is one of those random things that chemists know, and that you've always wondered, what is that even talking about? Is it an animal? Isn't this biology? What's going on? So a mole, you're going to find out, is a grouping word like the word dozen or gross or ream or something like that. But let's figure out what a mole really is. Well, to fully understand the mole, we got to talk about this guy. Look at him, Avogadro. Turns out he was Italian, and he was a lawyer for a while, but was like, psha, I don't want to be a lawyer anymore. I want to be a professor of mathematical physics. So he changed careers. And while he was getting this degree, he did a lot of research and experiments and work with gases and thinking about gas particles. And the thing that's kind of sad but interesting about Amedeo Avogadro, other than his face, it's interesting that he was working and thinking about atoms during a time when atoms were not even really believed to be true. It would be like if you opened up like whatever news source you like, so online or a blog or a podcast or a newspaper or whatever, and you read some story about unicorns and you're like, wait a second, unicorns aren't even real. How can we take this guy seriously? Well, that's kind of what Amedeo was running into. It was hard for people to take him seriously because he was talking about something that hadn't really even been widely accepted. And it turns out he passed away about 4 years before this was a widely known idea. So we talk about him in honor of the fact that he was really progressive and kind of advanced for his times. And about 4 years after he died is when atoms and a lot of his work became widely accepted. So because of that, when we talk about his work, we call it a hypothesis, because when he was doing it, it was a hypothesis. It hadn't been proven yet. Now it has been, but still in honor of that fact in his history, we call it Avogadro's hypothesis. So if you're taking notes, here's where I would start. Avogadro's hypothesis says if you have equal volumes of gases and there's the same temperature and the same pressure, they will have the same number of molecules. That's the hypothesis piece. Here's the details we can now fill in. We know that the volume has to be 22.4 liters. So if you have 22.4 liters of carbon dioxide and 22.4 liters of water vapor, at the same temperature and pressure, so like they're sitting next to each other on a lab counter, they will have the same number of molecules. Now, the temperature and pressure can't just be any degrees or any amount of pressure. It has to be something called standard temperature and pressure, STP, which means 0 degrees Celsius. So yeah, that's pretty cold. And then 101.3 kilopascals. Kilopascal is a unit of pressure. Think of it like air pressure or gas pressure, like pushing on a sample. I always think this is funny. 101.3 obviously is a very familiar radio station here in the Twin Cities area. I don't know how people remember standard pressure without KDWB. So we're so lucky. Anyway, temperature has to be 0 degrees Celsius. The pressure is 101.3 kilopascals, a unit of like, think of that kind of like barometric pressure, the pressure of the air around you. And it turns out that the number of molecules will be 6.02 times 10 to the 23rd. So this is like 6, and then you've got 0, 2, and then 21 more zeros. So 6, 0, 2, 0, 0, 0, 0, 0, 0, 0, like a huge number. So big, like, I mean, we really can't even comprehend how big that number is, but we're talking about something that is so small that we can't even barely comprehend it. So it makes sense. So it turns out that if you have 22.4 liters of gases at 0 degrees Celsius and 101.3 kilopascals, you will have 6.02 times 10 to the 23rd molecules. That is known as Avogadro's number, and it's equal to this thing called the chemistry mole. So mole is the grouping word for a huge number of particles, whether they're molecules or atoms or formula units. We'll talk about that later, but that's the idea of the mole. All right, go ahead and kind of process that so far. Take a little pause, write your level 1 question, think about what we learned so far, list Avogadro's hypothesis, or you could fill in the blank, or you could say, what temperature does it have to be for Avogadro's hypothesis to be true? That would be a great level 1 question, something that comes right from the notes. All right, welcome back. Now, here's the good news. Now that you know about Avogadro, there's some other things I can tell you about, such as, who is Amedeo Avogadro's favorite composer? It's Mozart. Okay, how about this? Where is Amedeo Avogadro's face carved? Where do they carve famous faces? Mount Rushmore. All right, a little bit of fun with chemistry puns. Okay, here we go. What do we do with this thing? This Avogadro's number, 6.02 times 10 to the 23rd, and this thing called the mole. What do we do with it? Well, it's a new way to count things. It's a new conversion. So we can say that 1 mole equals 6.02 times 10 to the 23rd atoms, if we're talking about elements. So we could say you have 1 mole equals 6.02 times 10 to the 23rd atoms of carbon, for example. Well, what if we're not talking about an element? Okay, well, what if it's an ionic compound? Metal plus nonmetal compounds, which remember are referred to as formula units. So you could say there's 1 mole of 6.0 equals 6.02 times 10 to the 23rd formula units, Fu, of sodium chloride. Sodium is a metal, chlorine is a nonmetal, so this is an ionic compound, Fus, instead of atoms, because an atom is for element. Formula unit is for ionic compounds. All right, what if you don't have an ionic compound? What if it's a covalent compound? A molecule. All right, so for example, 1 mole equals 6.02 times 10 to the 23rd molex, or molecules, of water. Water is made of all nonmetals, so that's a covalent bonded compound, a molecule. So those 3 terms are called representative units because they are the unit that represents that substance. Atoms represent elements. Formula units, Fu, represents ionic compounds. molecules represents water. So notice that the conversion is the same every time. 1 mole and 6.02 times 10 to the 23rd. Just like you would say 1 dozen is always 12. But it could be 12 shoes, 12 buns, 12 roses, anything, right? So just like in dozen language, chemistry language says 1 mole is always 6.02 times 10 to the 23rd, but what you're measuring changes. Okay, so why do we care about this? Because we measure things in chemistry, right? And we could be measuring different compounds or elements, and this tells us how many particles are we really dealing with. Let's practice one. So I could ask you something like, how many representative units are there in 1.1 mole of calcium phosphate? All right, so it is example time. All right, here we go. Same question. How many representative units are there in 1.1 mole of calcium phosphate? All right. Here's my given. So you're going to start these problems the same way we did the DA problems from before. You need a given, 1.1 moles calcium phosphate. So I did this for you. Calcium is +2, phosphate's an ion on the ion guide sheet, -3. So 3 calciums, 2 of that group, parentheses, all that good stuff. Calcium is a metal. I had to balance charges, ions, so that means that the representative unit that I'm dealing with, remember the 3 choices are atoms, molecules, or formula units. Well, because this is an ionic compound, metal plus nonmetal, the calcium is a metal, so Fu. So that means when I'm answering this question, I'm really answering how many formula units are there. The rest of it is the same that we've already learned. I need mole to cancel, so I'm going to set up my bracket. Mole has to go away, so mole is going to go on the bottom. So 1 mole. And I only have one new conversion that has representative units in it. That's Avogadro's number. 6.02 times 10 to the 23rd formula unit is the label. Mole divided by mole will cancel. I'm left with formula unit, which is a representative unit for calcium phosphate, so I'm ready for my equal sign. All right, now let's talk about how to type this in. Yep, you're going to multiply on the top, divide on the bottom. But remember, many of you have a fancy calculator like this one. You have this EE button above the 7 and then the second. So that EE is what you type in for times 10. So look at how I typed this in. 1.1 times 6.02 E23. I didn't need parentheses. I didn't need to type in times 10, caret button, 20, none of that extra stuff. So 1.1 times 6.02 times 10 to the 23rd. So I typed in 1.1 times 6.02 second EE 23. And then this is what it looks like. So that's how you use that fancy EE button on your fancy calculator. It makes your typing more efficient and makes it just easier to see what's going on. So then this means my calculator answer is 6.622 times 10 to the 23rd. That's what that E means on the readout on your calculator. All right, but we got to look at sig figs, right? So the calculator says this is the answer, but look, this only has 1, 2 sig figs. This has 1, 2, 3, but I can only keep 2. So 1, 2 sig figs. I look at this number for rounding, which it does not round. So this chops off 6.6 times 10 to the 23rd. Fu for formula units is my answer. All right, so there's an example of using DA with a chemistry conversion. All right, guess what we need to do now? All right, why did Avogadro throw out the bread from his refrigerator? Do you know? Yeah, it was moldy. Yeah, gross, right? Okay, and what does Avogadro learn in math class? What would he learn? Yeah, he learns how to multiply and divide, because why would you do one without the other? All right. Let's keep going. So Avogadro's number is okay, but it's really for just really, really tiny things. What about some other things? We need more than just Avogadro's number and mole. How about a new conversion called molar mass? Well, maybe you recognize the word mole in molar, and then mass is something we can measure in lab. So that's kind of a useful thing. So molar mass is the number of grams in 1 mole of some substance. Elements, compounds, doesn't matter what it is. You look at the periodic table, and for an element, the molar mass is the atomic mass, number of grams per 1 mole. So that line means per 1 mole. The atomic mass is the number on the periodic table, grams, for every 1 mole. However, if you have a compound, think about it. What do you think you might do to find the molar mass of a compound? If an element is just its molar mass, well, compounds are just elements combined. So yeah, you're going to add up the separate atomic masses, and then that's the number of grams for every 1 mole. So the number of the mass on the periodic table is your number of grams. And the thing that makes it molar mass is because that's the gram for every 1 mole. We always go to 2 decimal places because then no matter what periodic table you're looking at, the one I gave you, one in a textbook, one you printed from online, generally they're all the same to 2 decimal places. So for molar masses, we're just going to agree that we'll always do 2 decimal places, whether we're adding them up or just getting one element. So let's practice this. How many grams are in 5.0 moles of carbon dioxide? All right, so example time. Let's do it. I start with my given. So the good news is it's that same process. Start with what you have. 5.0 moles carbon dioxide, CO2. I want to get to grams, so I need to find the molar mass of CO2 because that's a conversion between moles and grams. Avogadro's number is not going to help me because I don't want to get to atoms or molecules or formula units. I want to get to grams. Moles and grams is called molar mass. So I look on the periodic table. Carbon is 12.01 grams per mole. Oxygen rounds up to 16.00, but I want those zeros, so I got 4 sig figs instead of just 2. It's grams per mole, but there's 2 of them. Add all of that up. 44.01 grams per mole is the molar mass of carbon dioxide. That is the conversion between grams and moles. And that's what I want to do, moles to grams. Okay, so I set up my bracket. I need moles to cancel. This is our conversion. So 1 mole goes on the bottom. 44.01 grams goes on the top. Moles will cancel. I'm left with grams, which is what the problem is asking for. So I'm ready for my equal sign. Multiply on the top, divide on the bottom. We get a calculator answer that says 220.05 grams of CO2. But this only has 2 sig figs. This has 2, 3, 4. But the rule says you can't be more specific than your least specific measurement. So I can keep 2 sig figs. I look at this number for rounding, which it does not. It stays a 0 for a placeholder, but I chop off the decimal places. 220 grams of CO2 is my chemistry answer because this matches the amount of specificness I'm allowed compared to the measurements in my calculation. Okay? So another conversion. So now we're using grams and moles instead of Avogadro's number, which was formula units or atoms or molecules compared to moles. So something a little bit more practical because grams we can measure in lab. All right, go and do a level 2 kind of question. You could make up a new problem like this. So you could say how many, either grams or moles, are in some given, make it up, pick a chemical. You could also use Avogadro's number. So making up a new example problem is an awesome level 2 question. Go ahead. All right, welcome back. Hey, we probably need to do some more of these, right? All right, what kind of tests does Avogadro really like? Yeah, he likes multiple choice tests, of course. And what did Avogadro wear to the prom? Well, the prom is kind of a fancy event, right? So, he's probably going to get kind of dressed up. So what does Avogadro wear when he gets dressed up? Think about it. Well, he wears his formal attire, of course. Yay! Okay, we need another conversion. Moles, not so useful by itself because it's just a random grouping word. Grams is kind of useful. Avogadro's number with atoms and molecules and formula units, that's kind of useful. But let's do another conversion. What about volume? All right, molar mass was moles and grams. Molar volume is moles and liters, but it's very specific. It's 22.4 liters equals 1 mole. But that's only true if you're talking about a gas at standard temperature and pressure. So if you're like, well, wait a second, how am I going to know it's at STP? It will have to be given to you in the problem. If it doesn't say STP, you can't use molar volume. You maybe would have to use density, which has volume and grams in it. But if it is at STP, you can use this very specific conversion. So for example, what is the volume of gas at STP of 0.30 moles of oxygen? All right, example time. Let's try it. I start with my given, just like always, 0.30 moles. Remember, oxygen is diatomic, so when you write the symbol, it's O2. I want to know the volume, but it is at STP, so molar volume can be used. So set up your conversion. Moles needs to cancel, so it has to be in the opposite spot, so I'm going to put it on the bottom. And because I'm trying to find volume, and it's at STP, I can use that new conversion, 22.4 liters. Moles will cancel. I'm left with liters. That is a unit of volume, so I can do my equal sign. I don't have to change it into milliliters or anything else because it just says volume. Multiply on the top, divide on the bottom, you get a calculator answer that says 6.72 liters. Okay, so then this is something we can imagine. This is, imagine this is a little bit more than like 3 2-liter bottles. So you can get a visual of what 0.30 moles of oxygen would look like. So something a little bit, again, more practical. Liters is something we can kind of imagine. We got to do sig figs though. This has 2 sig figs, but this has 1, 2, 3. Our final answer can only have 2. So I can keep 1, 2. I look at this number for rounding, which it does not. So chop off to 6.7 liters of oxygen. Another conversion. Okay. All right. Guess what? Let's keep going with this. What is Avogadro's favorite Disney movie? Now, this is an old classic one, but I think you might have heard of it. There's this girl who, she's kind of mad at her dad because he's kind of holding her back. What am I talking about? Avogadro's favorite Disney movie? The Little Mermaid. Oh, he just loves it. Yay! All right. One more conversion. What if we want to know about atoms or ions in a compound? So we don't want to just stop at atoms, right? Like atoms if it's an element. But what if we have a compound and we want to know how that compound splits into atoms or ions? We know that there's 6.02 times 10 to the 23rd representative units in 1 mole. Well, there could be some number of atoms in 1 representative unit. Now, if it's an element, then it would just be atoms. You're done. But what if that representative unit is splitting up into atoms? Because remember, representative units are compounds, either formula units or molecules. But then you also would just count up the atoms in that compound, or you would count up the ions in 1 formula unit specifically. Because remember, molecules aren't ions. So when you dissolve something in water, it splits up into its ions. That could matter for precipitates or conducting electricity, little ions floating around, or like water softener solutions need to split up into ions so that they can replace hard water ions, all that stuff. The number of ions could really matter for a chemist, what they're doing. So you count the total positive pieces, the total negative pieces. So it's not counting up all the atoms, just how many positive ions are there, how many negative ions are there. So for example, how many ions are in 0.11 moles of sodium chloride? All right, example time. Let's try that problem out. So first of all, I start with my given, like always, 0.11 moles of NaCl. But this time the problem wants to know ions. Well, here's the tricky part though. Ions are not related to moles, but ions are related to formula units, and formula units are related to moles. All right, so I know that sodium is +1 and chlorine is -1. That's where sodium chloride came from. So that means there's 1, 2 ions in 1 formula unit, right? So 1, 2 ions in 1 formula unit. But I can't use this conversion yet because my given is moles. So I have to cancel moles. This brings us back to our first conversion today, Avogadro's number. Moles is going to cancel, so I'm going to put that on the bottom, and then I'm going to put 6.02 times 10 to the 23rd formula units on top. Moles will cancel, and now I'm at formula units. But the problem was asking for ions because this will split apart when it's dissolved in water. So then I need one more conversion, but this time I need to cancel formula units. So I can use this conversion. 1 formula unit on the bottom equals 2 ions. So you have twice as many little pieces floating around, and that could matter for lots of different chemistry situations. Formula units cancels, I'm left with ions. That's what the problem is asking for. So now I'm ready for my equal sign. Multiply all the numbers on the top, divide on the bottom. Remember, use that fancy E button. So you would type in 0.11 times 6.02 E button 23 times 2. The calculator gives you this big long answer, but look it, this only has 1, 2 sig figs. This has 1, 2, 3. This is an exact definition. No error in counting the number of ions, so there's no sig figs with this. So I can keep 1, 2 sig figs. I look at this number for rounding, which it does not. These chop away. They're not science answers at all. They're just math answers. And so the science answer is 1.3 times 10 to the 23rd ions of sodium chloride. Don't forget to look at the end of your calculator for that times 10 to the 23rd. If you just gave me an answer of 1.3, that would look weird because you can't have a decimal place of an ion and it's a super small number. That doesn't make any sense either. It should be a huge number if we're talking about tiny pieces like atoms or molecules or formula units or ions. All right. Okay, go into your level 3 kind of question. Maybe make a prediction of when this kind of math would be useful in chemistry, or do an argument or any type of level 3 question. Summary would also work. All right. Hey, before you leave and go practice, I just want to make sure you have all the tools you need in one spot. So you can just listen and take these a screenshot at the end, or you could write this down as we go. Here's the full list of the conversions that you'll be using. Avogadro's number is if you're going back and forth between moles and representative units. 6.02 times 10 to the 23rd representative unit equals 1 mole. Representative units would be formula for an ionic compound, which is metal plus nonmetal elements. Molecules for a covalent compound, nonmetal plus nonmetal elements. Atoms is if you already just have a single element. That's how you'll know which representative unit. But the number and conversion is always Avogadro's number, and it's always equal to 1 mole. Molar mass is if you're going back and forth between grams and moles, and you get the number from the periodic table of grams equals 1 mole. And remember, we're going to 2 decimal places, and the blank get filled in from using the periodic table. Molar volume is another conversion between moles and liters, but remember it is only true at STP, but it's 22.4 liters equals 1 mole. If it's not at STP, I mentioned this in passing that you might need to use density because density is a conversion between mass and volume. So you could go from moles to volume and then volume to mass, or you could be given moles and be asked to get to volume. So you could go from moles to grams using molar mass and then grams to volume using density. So just realize if you're given density, that is a conversion between mass and volume. And the other one you might be asked is about ions in a compound. Ions equal 1 formula unit. Sorry, this shouldn't be on here. Ions do not equal molecule. That is a typo. Ignore that. Ions equals 1 formula unit. And to find that number blank, you count up the total positive pieces and the total negative pieces. So for example, calcium phosphate is 5 ions equals 1 Fu. Why is it 5? Because look, you have 3 calciums, a plus, and a plus, and 2 phosphates, a negative and a negative. 1, 2, 3, 4, 5 ions in 1 formula unit. Whew. Okay, that was a summary of all the stuff we just kind of learned about today. So take a screenshot of this, pause the video, and write it down. Here is your new list of conversions. All the DA and all the math is the same as we were doing before. It's just that these are your choices for conversions. And we probably should end with one more of these. All right, what does Avogadro put on his pancakes? Yeah, molasses. And how does Avogadro get across the desert? On a camel. All right. Thank you so much for your focus. Lots of new details today. Here's your to-do list. Go back and finish any Costa questions, write a summary for today, and then you can start working on the mole practice assignment, but only do numbers 1 through 4. 5, 6, and 7 are new topics for different days. So you will not finish this. Don't try to finish it. That'll just kind of stress you out. No reason to teach yourself. I will teach you how to do the other problems on different days. You could also look at some unit practice problems, 13 through 32. The answers are posted so you can check your work. You can get immediate feedback just to see if this new stuff is making sense. But please make sure you do either number 3 or number 4. So either start on the assignment, even though it's not due for a while yet, or do the unit practice problems to make sure this new stuff today is making sense so that you can come on Monday with questions, or you just know you're doing it right before we move on. Okay, and then I do want to make sure if you are watching this video on the day it was assigned, your types of reactions lab report, which remember is just the handout, is due today. So don't forget about that. All right, thank you so much for learning about more chemistry with me, learning about mole chemistry with me. We'll see you next time. Bye.